Okay, for number 61, it says sketch the graph of 1 over 3 to an x. We looked at this a little bit before, right, in number 59. So we know that as x gets larger, 1 over 3 to the x gets much smaller, right? And for x less than 0, we would take our base and shift it up into the numerator, right? Because x3 to a, let's say, negative 2 is the same thing as 3 squared, or 1 over 3 to a negative 2 is the same thing as 3 squared. So whatever's in the denominator gets shifted up to what is in the numerator. So then as x gets much smaller, as x gets more negative, our function increases. So that's what it looks like in number 61. All right, number 62, you could take logs of both sides and bring down the power, but an easier way to see this is that 25 is equal to 5 squared. The only way that you could have a base to a power be equal to another base to another power is if the powers themselves are equal. So I could just write it with common bases and then say that x minus 4, in order for 5 to an x minus 4 to be equal to 5 squared, then my exponent of x minus 4 has to be equal to 2. And then it just becomes solving a linear function, right? So x has to be equal to 6. All right, number 63, you have to know that that e to an x is never equal to 0 for all x in our real number system. So that allows me to divide this whole thing by e to the x, because I know that I can't divide by 0, but since e to the x is never 0, then it doesn't really matter. So this cancels out with this, and 0 over anything that isn't 0 is just 0. Gives me this. And then it's just a matter of factoring x squared minus 5x. So I have x times the quantity of x minus 5 equal to 0, and that occurs when either x is 0 or x is 5. Okay. In number 64, I could use, again, logarithms to find out what x is. Instead of doing that, let me try to write everything in a common base. So 27 is the same thing as 3 cubed. 1 over 9 is the same thing as 1 over 3 squared. Multiply both sides by 3 squared times 3 squared times 3 squared. This cancels out with that. And then 3 cubed plus times 3 squared, add the powers together, we have 3 to a fifth equals 3 to a 2x. Again, the only way for me to have 3 to a fifth equal to 3 to a 2x is if the two exponents themselves are equal. So therefore 5 has to equal 2x, so x equals 5 over 2. Again, with number 65, we're doing the same tune. And we're trying to write everything in common bases, and then solving when those exponents themselves are equal, and I get this. The general way to do it would be to actually take logarithms. So let me just show you that real quick. 3 to x equals 4 to a 1 minus x. I could take a natural log of both sides. 2 to an x equals natural log of 4 to a 1 minus x. It wouldn't have to be a natural log. It could be a regular log, like a base 10 log. Then I can bring down the power, right, on both sides here. This gives me x times natural log of 2 equals 1 minus x times natural log of 4. Distribute the natural log of 4, so I get natural log of 4 minus natural log of 4 times x. Put all the x's on the same side, so I would get x times the natural log of 2 plus the natural log of 4 times x equal to natural log of 4. Factor out the x from both of these two terms, and I would get x times the natural log of 2 plus the natural log of 4 equals the natural log of 4. And therefore x would be equal to, divide both sides by this quantity, natural log of 4 divided by natural log of 2 plus natural log of 4. But I can guarantee you that this quantity here is exactly equal to 2/3. Has to be. So try it out if you want. Take out a calculator, blah, 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 blah. But it is. Okay, we'll start off on number 66 in the next video.